two standard very small seminars, and also a presentation, a quick one, of something that we do in our team, and that is a precise request of the coordinators of your course di laurea. I'm not terribly agreeing with that, but I have been invited to show activity in topological data analysis, so that will be the last part. But before, I just want to show you a couple of things. One, configuration spaces. One, and second, small words. So, configuration spaces. We are, you have, not in graph theory, but in geometry and in linear algebra, you have been exposed to high-dimensional spaces, and you might have wondered, why should I consider high-dimensional spaces where the space I live in is just three-dimensional, and come on, four-dimensional if I had time? Well, the idea is that actually the geometrical spaces, even a higher dimension, are very good for representing situations in which you have that each configuration is described by n parameters, okay? And so we might have something three-dimensional just considering our perception of colors. Is anybody here colorblind? Okay. About 8% of the male population is colorblind in a weak way. What does it mean? What happens? The thing is that don't be misled by physics when thinking of color. If you're thinking in terms of physics, the color of a photon, of a light beam, is just tied with the wavelength, okay? But it's not like that for us, meaning that our impression of colors is completely contained in our visual system, meaning from eye to the visual cortex here, okay? And my impression of red, my impression of blue, and so on, is not something which is outside of me. Red, this red, which I see and you see, is only present because we are seeing it, okay? It is a reaction of three types of receptors that we have in our retina. Actually, we have four. One, in this moment, is out of order in the sense that it only works when the light is very, very dim, okay? And I invite you to see the activity of these rods when you have all lights are off in your house and you just have few lights outside, and you may see that you cannot recognize colors. Before you turn off the lights, take two very bright colored things, one red and one blue, for instance, and you'll see that you cannot recognize them. It's everything is more or less bluish, and it's because your cones are not working and the rods are working. Now the rods are not working and our cones are working, and the cones are they have these curves of answer to the frequency or the wavelengths, if you want. So you don't have something going monotonically in the sense that the higher the frequency, or in this case, the higher is the wavelength and the higher is the response of these cones. On the contrary, they are more or less Gaussians, okay, with peaks on particular wavelengths or frequencies, okay? And so you have sensation of what you have in front of you, just by the mix of these three responses of the three types of cones that we have. Okay, and the most common type of color blindness is the lack either of pigment 530 or the pigment 560. These two, sorry. Oh. Okay, I don't know how to. All right. So either this or this is missing. Okay, and so what you have is that red, yellow, green all look to them a bit like sort of yellow or brownish yellow. Okay, and so they cannot recognize. I hope I don't offend anybody, but please think of being God. Okay, how would you plan? Would you design the visual system with these peaks or in a different way?
You have to break away.
How?
Linear response.
No, you have only to work with peaks. Yeah, it's something with a peak of response on that, and that. But there is something I don't like as a little god. Okay, I don't like in this situation. Sorry, I need to know something. Is anybody creativist here? I don't want to offend anybody in terms of religion. I mean, can I talk in terms of Darwin's evolution without offending anybody?
Yes.
Okay?
Yes.
All right. So we all believe that somehow Darwin was right. Okay? And so what happens is just the fruit of evolution. If I were God, I would put those two peaks a bit farther apart. Why? Because this would mean a better response to different colors. Okay, the more they are equally at equal distances, the better is the distinguishing capacity, ability. Okay, and how did these two come? That's very interesting. The evolutionists have interpreted this by looking at birds and what can be known of the dinosaurs. Okay, at the time of dinosaurs, mammals were very little night animals. Okay, so we didn't need many receptors. Okay, color was not that important for us. Okay, but then the big beasts all died, and we found a whole world at our disposal, so we became also daily animals, okay? And what happened was that at a certain point in evolution, big primates had the possibility of developing that by, say, a mistake of DNA reproduction, okay, where you had that a single type of receptor just doubled. You can see that by these very close peaks, okay, so near each other, okay, that it might be actually an error in reproduction where you have that one has split into two close together. But the effect was enormous, because at that moment you could recognize a ripe raspberry among the leaves, okay? Whereas a colorblind, I have a friend who's colorblind in exactly that way, and it's funny because we were looking for I don't know the name. Okay, some type of berries, very bright red, And he couldn't see it in the leaves, and I could pick them up and say, okay. And that is a great evolutive possibility, of course, just because of that doubling, okay? But let's come back to us. What I mean is that you don't have that one cursor, so to say, along the wavelength when you have to reproduce or induce the color sensation in humans. And that's very important if you build a monitor, if you build a screen, of course, because you must take in consideration who's going to look at that, your dog or you. You are paying, the dog is not paying, and so they adapt the production of colors to your receptors, okay? And that's why we have RGB, okay? Exactly because they are tuned to those peaks of response, okay? Just because that's the best way to know in advance what type of color you will see inside your head, okay? This means that actually colors, as we normal seeing humans perceive them, are given by three coordinates, which are the three responses of the three types of receptors. Okay, and that is important because in a color image, what you have, if you have it not, if you have a bitmap. Okay, you know what a bitmap is? Okay, instead of JPG or GIF. Okay, so bitmap, the very raw matrix of pixels. Okay, if they are in color, what do you have? You have that each pixel contains three coordinates: R, G, red, green, and blue, from 0 to 255. Okay, and so you have for each pixel a point in a three-dimensional space. Okay, so actually this is the cube which we can draw in space, which has here hidden black there, and here we have white, and then we have all possible colors reproducible on a computer screen. Okay. And that's why we have the possibility of seeing a color like a point in three-dimensional space. That's for humans, but birds have four types of receptors, and not only they can see ultraviolet, okay? Okay, that's an advantage if you want. But there is another more subtle advantage, which is the fact that their vision, their color vision, is four-dimensional, whereas ours is three-dimensional. So even if it were just inside the range of frequencies that we can see, they would have a much richer sensation of colors. And exactly, we are, in a sense, colorblind birds, okay? Meaning, what a colorblind human is to us is what we are in comparison to birds, and not only birds. And what does that mean? It means that if you have, if you cut that cube at a constant brightness, so the sum of the three coordinates, you can take a plane of a constant sum of the three coordinates, x plus y plus z equals fixed k, okay, then you can have an idea of what happens, and you have, of course, a triangle, not all filled, okay? This is what we actually can see. But if you do the same thing for a bird, you have to cut a four-dimensional cube, of course. And so what you get is not a triangle as for us, but a tetrahedron, a triangle of pyramids, okay? And so you see that already, if you want to conceive and to work on colors of the bird, you have to go to 4 dimensions without time. It's not time. It's just that the parameters that you would need for representing numerically the sensational color of a bird, you would need 4 parameters, and this means go to a 4-dimensional cube, and if you cut to a 3-dimensional tetrahedron, okay? And this is already the first idea of configurations. But configurations can be even much more simple and more closer to us. Let's see this situation. You have two bicycle runners on a certain road, okay? They have started in point 0 or O, if you want, okay? And they are at certain positions, all right? They are 2, and of course the situation is 1-dimensional. It is that road, okay? The road may be curved, okay, but you just have that. If you want, you need only 1 parameter to say where a person is. The distance along the road from O, all right? But if you have 2 people, then you could do something which is this. Create a completely artificial plane, which is not the plane where the road lives, okay? It is an artificial plane in which just 1 point represents the 2 positions together, meaning that these on this and on this axis, both are the same length, but one is referred to runner A and the other to runner B. And so you have that this point means the position of the 2 along this curve. Okay, so we are simplifying in a sense, meaning we have, let me say, a complicated configuration in a simple space. The very simple space is the curve, where we have the race, okay? And that's very simple. But we have, let me say, a complicated situation because you don't have just 1 person, but you have 2 people, okay? And you do what? You want a single point. Is it possible? As you know, since you are grown-up people, you never get anything free. You have realized that in your life already? Okay, remember that. You never get anything free. So you want to have a point instead of 2 points, you must make a compromise, okay, a trade-off. What's the trade-off of getting just 1 point instead of 2 or 3 or 4 or 100? It is that you make the space more complicated. So the geometry of the space absorbs the complication of the configuration. So you will always have just 1 point instead of a complicated situation. And it's the space itself which absorbs the difficulty, in a sense. I'll be more explicit in a moment, okay? For instance, let's see how we could exploit this thing of representing in an artificial plane positions of 2 runners. One possibility is think that we want that B is 1 unit further than the runner A. Okay, so XB equals XA plus 1. But this becomes a very simple right line in our plane. This is an artificial plane, and this means all the positions of the 2 runners respecting this constraint. Okay? Another constraint might be this blue one. Let the distance of points A and B from O be no more than 1. And this is constrained but inside this blue square. Okay? So if you want that both constraints are respected together, then you just make the intersection of these 2 geometrical objects. There is no square in the plane where the road is. There is no red line in the plane where race takes place, okay? It's only abstract, but then I can know that there are an infinity in this segment of configurations in which the two things are respected, okay? If, for instance, I set that B must be 2 units further than A, I will have that other line, and so I know that only one possibility is given. If I put 3, then I know that the line will be here. There is an empty intersection with the blue square, for instance, okay? If you, I don't think you remember first year linear algebra, but you might, I don't know, I would hope so, because I'm mainly a first year linear algebra teacher. And what you have there is a theorem telling you how you can have intersections of different objects in space, okay? And so if I take in the plane, I take 2 right lines. What do we have? One equation in 2 unknowns, one equation in 2 unknowns, linear equations. And so I might have rank 1 and 2, no intersection, parallel lines. Rank 2 and 2, exactly 1 intersection, lines incident in 1 point. What happens in dimension 3? What about 2 right lines? 2 equations in 3 unknowns, okay? But I might have 3 and 4 as ranks of the incomplete and complete matrices and no intersection. I might have 1 and 2 again, no intersection. I might have 3 and 3, 1 point of intersection. What happens if I have one right line and 1 plane? Okay, again I have 2 equations for the line, 1 equation for the plane, and again I look at the possible ranks and I find they either have no intersection, or the line lies entirely on the plane, or they have 1 point in common. What about 2 planes? That's easier in dimension 3. Can I have 2 planes intersecting in 1 point? No. Why? Because 1 plane, 1 equation, another plane, another equation. So 2 equations in 3 unknowns. What's the possible disposition of ranks? 1 and 1. The 2 planes coincide. 1 and 2 planes are without intersection and they are parallel. Last only possibility, 2 and 2. That's the last possibility for the ranks of the 2 matrices. And this means 3 minus 2, that the intersection is a line. So in free space, 2 planes may not have a single point of intersection. Either none point of intersection or a line of intersection. Okay? So one might ask, what happens if I go above with the dimension? Can I have, for instance, in dimension 4, can I have 2 planes meeting at a single point? Well, in dimension 4, a plane is given by 2 equations, and a plane by 2 equations. Okay? So I get, if I put everything together, 4 equations in 4 unknowns. All right? Could I have a single point? Sure thing. If the determinant of the incomplete matrix, which is square, is different from 0. So it's possible to have, in 4 dimensions, 2 planes with just 1 point in common. Okay? I could show you how to imagine that with the help of time. But I prefer to say, can we have that in terms of configuration spaces? Sure. Now if we have a dimension 4, it means I don't have only 2 runners. I have 4 runners, all on the same road, okay? And I have 1 coordinate of my point in dimension 4, representing the position of each one of the 4 runners, okay? So every configuration of the runners along the road will be 1 point in dimension 4. Now, can I have this thing which I said? What does that mean in these terms? Look, say for instance that we want that this is a first plane, meaning we are in dimension 4 and I have two linear equations. So this represents a plane. What's that in terms of my runners? It means that the middle point between A and B is in position -3, and the middle point between C and D is in position 1. Okay. Another plane is this, that C is 5 units further than A, and D is 1 further than A. Okay, but these two constraints mean a plane in dimension 4, two constraints mean a plane in dimension 4. I put all of them together and I get only one position, one configuration, one point in dimension 4, which means this configuration of A, B, C, and D on our road. Okay? So it realizes something which we have very big difficulty in understanding, imagining two planes which have a common point. All right? Next is something which I will not tell you, which is of topological type, but okay, let me go to this. In robotics, the first being old gives me some advantages. Life for an old person is like a time machine, okay? So I was able to visit very ancient times in which robotics was at its beginning, okay? And at the beginning, what you had when you had the problem of path planning for an autonomous vehicle, for instance, was that you just used a single point representing a robot, okay? And that's fairly understandable, okay? First thing, you want to have a point, and you want it to avoid obstacles, you want to, okay. And so a single point is all right for many things. Not always, anyway, because you have that a door has a width, and so I should take into consideration, into account, also the width of the robot itself, okay? And so a further approximation might be not to use a single zero-dimensional point, but a disk, okay, with the diameter which is the diameter of the robot itself, so that I know whether it can go through the door, whether it can go here, okay, a point would go here, but I cannot go here because I have a non-zero dimension, okay, and so I need to know also, the next thing was to use a disk, but eventually, actually rather soon, they realized that also the shape has an importance in moving things, okay? I don't know whether you have, are you all, no, you are, some of you might be living at home in the original family, the Italian ones. Oh, what an unfortunate thing. But all the others might have the experience of living in a flat with other students or such things, okay? And then you might have this problem. You have a table in this room and you have to take it to the other room, okay? And it does not go. So you get a wonderful idea. You tilt the table and make it go first with the legs and then with the other legs. So by some maneuvers you can get the table through the door, okay? And this is a well-known, a very important problem. And they had, I think they still have, a way of talking about that. They call it the piano mover problem, meaning that you have a piano not just a single keyboard, but with the one with the big tail, okay, so with that irregular shape, and you have to move it among obstacles, through doors and such things. So you will find, Google it, and you'll find piano mover problem, quite a lot of papers on that item, okay? So let's have a piano mover problem which is very, very simple. This one. So I have a corridor, bending corridor with my piano on a platform, a turnable platform, but the platform itself is on a rail, okay? So I have two things to take into consideration: the position of the platform along the rail and the orientation of the platform around its position on the rail, okay? So the position on the rail will be one parameter which goes from a certain number to a certain other number. And so you can represent it just by a point on a segment, okay? The orientation can be given, say, by the angle between the keyboard and the rail itself, for instance, okay? All right. And angles, we are not winding things around. So being like this or being like this, I consider the same. All right. If I had a rope, that would make a difference. Okay. No ropes. So here or here is the same. This means that I have that my position is given by an angle with 0 equal 2 pi, or if you prefer 360 degrees. All right. What does that mean? It means that the position of the keyboard for a given position on the rail is given by a circle. So you have together a position on a segment and a position on the circle. This means what is called the Cartesian product of circle and the segment. And that is given by a piece of cylinder like this, okay? So what you have, is that a single position, complete position of the keyboard is given by a point on the cylinder. Again, there is no cylinder there to be seen, okay? The cylinder means every point in the cylinder means a configuration of the keyboard. Okay? For example, position R with respect to the position on the rail is here, S is here, and T, the final one, is here. R as a position as an angle is this, S is this, and T is that. As you can see, they are opposite with each other here and here with respect to the rail. But if you mix them together, you have that this point in the cylinder means the complete configuration of R, that the complete configuration of S, and that the complete configuration of T. All right. And then, what should I care about that? I should care because here the corridor is wide, but here the corridor might be narrower. If it is wide like this, if I want to plan how to go from this position P to this position A, I can go wherever I want. Why? Because all angles and all positions on the rail are admitted. Okay, the corridor is wide. Wherever you are, you can turn the piano around at any angle with respect to the rail, and so it's all allowed. It's all blue because every point in the cylinder is a point which can actually represent a legal configuration of the piano. Okay? And so if you want to plan how to go from here to here, you can say, well, go along, and while you are going, slowly turn the the platform, okay? Maybe you go a little bit beyond, so you start like this, and you go like this, and you're going a little bit beyond, and so you end up with the correct angle. All right, but think that it is narrow like this. But fortunately, you can make that, you can, oh, well, when you are here, it's in the correct position for turning around. And so now quite a lot of configurations are forbidden by the width of the corridor, okay? Only the blue ones are allowed, and mind, here you would have that you cannot go if it were the other way around. But here you are lucky, and then you do what? You go up to here with the same orientation. This means like this. When you are, up to the end with the same orientation with respect to the rail. So this angle, okay? And when you are out of the corridor, here, you just turn the platform. So it means I'm like this. I go, I go, I go, I go, I go. I'm out now. What happens if I am in the other situation? I cannot do that because it will not go through. So I'm here now, and the same trick as before is forbidden to me. Okay? Now consider, I know that in this case, even a child of, I have a granddaughter of 4. I must do this experiment. I was almost forgetting that. But I must do this experiment. I mean, I don't know whether my little Agatha would be able to solve this. You are here, you have to go there. What do you do? Okay? But surely, absolutely surely, she would solve this other problem. You are here in this point, you have to go to that point and always stay on blue. Don't you think that a 4-year child would solve this? A 3-year, a 2-year child would solve this. Go without interruption, always staying on blue from P to A. I am pretty sure of that. And so you can see that this is the solution. How can we interpret this solution? We interpret it like this. You would like to go there, but instead you go in the opposite direction. Okay, I'm here, I should go there, but I go here. And now I turn, and then I can go up to the end. This means go in the opposite direction. Turn completely around by staying in the initial end point of the rail, then go along the rail, and then you can turn the keyboard at the end. Okay? So you simplify your problem. Can you see what I was meaning? We have a sort of complicated configuration in a simple space. Okay, our plane with a corridor is a simple space, but a complicated situation because I have a position along the rail and an angle with respect to the rail. It becomes just a point on a cylinder where I have forbidden and allowed points. But then the problem simplifies itself quite a lot. Okay? Look at something more close to your professional activity, maybe. And so a robot with some degrees, in this case 6 degrees of freedom. Okay? And I want to put the end effector, which is here, in the wanted position in space. Okay? Just think of the position without orientation, which would make things still more complicated. Just put the end effector in the position. And we have to consider that we have some horrible things which are dead points. Yes, but you have the little acquaintance with mechanical things. But maybe you have a driving license, okay? And so you should know what a dead point is. Anybody does not know what the dead point is in a car motor? It is when you are with the piston at the end of its race. Okay, you have the explosion and it comes down. You have that. What you have is that the motion, the rectilinear motion of the piston must be converted into a circular motion of the motor tree. I don't know whether that's the name. Okay, and that's possible, of course. But when you are at that point, so when it is like this or when it is like this, it has to decide whether to go on one part or on the other part, okay? And that's why you have, I don't know the name again in English, but you have a massive disc attached to the motor tree, okay? Why? And it is the one which you put in motion by the ignition, all right? You put it in motion with a small electrical motor, okay? And then it accumulates angular momentum, and it is what solves the problem of dead points in a motor, because when it is like this, that it pushes down vertically, this object gives its angular moment to the tree, and so it decides that it has to go this way instead of that way. So dead points are terrible for mechanical things, okay? And you get, how can you interpret, how can you discover dead points, how can you avoid them also? Consider a very simple, very simple robot arm like this. You have it on a plane, you have that this point is fixed, and you can rotate this arm up to this sort of elbow at any angle with respect to the vertical, okay, any angle alpha, and so you have the position of this elbow P given by what? By this length L and the angle alpha, okay? Attached to this, with the possibility of having any possible angle beta, you have this forearm and this hand effector Q here, okay? And so what you have that at the pair of angles, you make a point Q in the plane correspond. Okay, so you have a function from alpha comma beta to x comma y. All right, and be careful, because you might have two different configurations of the arm giving the same end position Q. Okay. And so this function is not injective, meaning that you have different pairs, alpha beta and alpha prime beta prime, giving the same point xy. Can you express this in geometrical terms? Well, sure. If you have all possible pairs alpha beta, which are angles, you are making the product of two circles. The product of two circles is not a sphere as you might imagine. It is a torus like this, okay? And so all pairs alpha beta of angles correspond to a point here in this geometrical object. Our function f gives to a point on the torus a point in the plane, okay? And you might have actually two different configurations of the robot arm giving the same position of the end effector. And there is these two circles are important. Why? Because what you have is that if you have, look at this. Try to think that I want to clean something with the point Q. I want to clean a small area, okay? And then what? But remember, we are so used to our what is called inverse cinematics that we actually, well, my kung fu master, Wushu master,
Yes.
okay, always says it's the finger which must go. Don't think of your arm, don't think of your hand. It's the finger which drives your movement, okay? And it's what is inverse cinematics, meaning that I'm so used to this fact that I want to touch this. Okay, look at how good I am. Very normal. But what have I done? I have actually given orders to a set of muscles making angles, this angle, this angle, this angle, all angles driving me to this, okay? And that's rather difficult if you want. All right, but I have to work on these angles. In this case, I can work by modifying alpha and beta, okay? And look, what do I have? If I wanted to clean a little patch around Q, I can. I'll take a neighborhood of or my point alpha beta here. Say this. I take a neighborhood here, so I move alpha and beta a little bit, and so by covering a patch here, where we can think in the tangent plane of this torus at that point, I cover a little neighborhood of position of configuration alpha beta, and I will cover a little patch of plane here, okay? Only if I'm far from the dead points. Where are the dead points? Look at this. If I am here, it means that my arms are stretched like this, okay? Just think of two parts as in my picture, okay? And I have just two parts. If it's bent, I can work on this angle and do like that. But if I'm like that, if I work with this angle, I polish just a small curve. If I use this angle, I polish just a small curve. I use this both, I just polish a small curve. How can I take this intuitive idea into mathematical things? It's easy. It's because if I look at what happens to the tangent plane here, it goes to a tangent plane here. But if I take the tangent plane here, it goes to a tangent line there. Okay, it reduces its dimension. So if I take the differential of this function f, I'm linearizing the situation, and I look exactly what happens to the tangent planes. A tangent plane goes to a tangent plane. Okay, tangent plane goes to something of lower dimension. It goes to a line. That's that point. That's where I cannot do what I was trying to do. How can I find them? Look at the computation. What's the position of P? It is L cosine of alpha, L sine of alpha. That's easy, okay? That's the position of the elbow. Once you have the position of the elbow, what's the position of the hand? The previous position plus M cosine beta, L sine alpha, which we had already, plus M sine beta, where M is the length of the forearm. Okay? Okay, let's do this. This is X, this is Y, this is my F. I can make the Jacobian matrix. I get this. What does the Jacobian matrix mean? It means what happens between the tangent plane in the domain and the tangent plane in the range. And so, if I have that the rank diminishes from the maximum possible 2, it means that a tangent plane goes to a line. Okay, exactly what I wanted. And that's given by the determinant of this matrix and the determinant in this. And so you have those terrible points when this sinus is 0, which means either so also, okay, now, couldn't we have 3 parts of my robot arm? Sure we could. And now we are already in dimension 3, something which I cannot really see as I was seeing before. But the computation is the same because I have now this longer way of taking alpha, beta, and gamma to 2 points in the plane, okay? And this is the Jacobian of this transformation. And again, I want the rank to be 2. Now I have to make 2 determinants vanish. These 2 determinants give me all the positions where I have the same problem, okay? Giving me, again, the dead points, okay? No, this I already showed you. Now, I would have liked to show you small words, but as my coordinators would like, I show you instead, and I'm not so unhappy of it, because the request is to speak about the research of my team. Actually, I'll not show you what is in the title, non-topological persistence, but I'll just tell you the initial part, which I've done, as you can see, this webinar a few days ago. Okay, and the initial part is just persistent homology, okay? And so I show you only this and not our recent progress. The initial part was, maybe you know persistent homology, let me recall the basic things, okay? And so you do not know persistent homology, I give you the basic things, okay? Okay. What we have in pattern recognition is generally for computer vision, pattern recognition in general, that you there are 2 ways substantially to make a recognition. One way is direct on the images, okay, in the sense that I try to I want to recognize this thing, okay, but I am looking at it from an angle, and so what can I do? I can try to use some matrices to do perspective transformations. It's possible, okay, it's not that difficult, but it's rigid in the sense it's very good for mechanical objects like this, all right? Recognition of mechanical objects, recognition of defects of mechanical objects can be done with the linear algebra of your first year, or a little bit more than that, an extension of that linear algebra you met in your first year, okay? But if you have natural images, for instance, you cannot have a matrix superimposing this picture of mine with this picture of mine, okay? You cannot. You could do it, there are tricks. Take pieces, because I'm not an octopus, I'm partly rigid, okay? And so you can have a sort of composed object, and each of the parts is rigid. So you can make tricks like that. But it's not the freer possibility. There is topology, which is actually much freer, but maybe too free, in the sense that there is a topological transformation taking me like this to taking to me like this. Okay, no problem. But there is a problem, which is there is a joke, which is not actually a joke, but a terrible truth. For us topologists, a mug is the same as a donut. Okay, the one which you should put into the mug for your breakfast, okay? Why? Because you can continuously form one into the other, as you can see. All right? And this means, all right, so there is a freer idea of shape, but too free. It's so free that you can confuse, you can have a transformation from mug to donut, and so you will not be able to recognize the two, okay? But we have some 25 years ago, a little more, devised a way of doing that, of using topology together with geometry. And the idea is this. Consider an auxiliary function defined on your objects. In this case, just minus the ordinate, the height, okay? In the sense that I turn, if you want it, I turn the mug upside down, and then I take height, okay, as a function. And then I take all what are called the sub-level sets at each level. And I have something which is good for topology. Topology looks for holes of the different types. For instance, there is what we call one cycle, which is like something like this, okay? And a two cycle like a balloon, or like a torus as before. So a void inside something, okay? So two different types of voids. Either this hole, or you know the Gruyere cheese, Emmental cheese. It's a cheese which forms big empty balls. Actually, they are full of gas. Okay, all right. Okay. Two cycles are these holes. One cycle is, for instance, this of the donut. Okay, which is the donut is something like this from topological point of view. Okay, so topology counts different pieces called connected components, again as in graph theory, 0 cycles, 1 cycles, 2 cycles, like the holes in the Emmental. Okay, so if you just take the sub-level sets of height, here I see something. I see a 1 cycle for the mug, which is not present for the donut. I go up and then I get 2, because this is a 1 cycle and this is a 1 cycle, whereas the donut only has now a 1 cycle. And at the end, this has 2 1 cycles, sorry, just one cycle, because you have the bottom of the mug which closes one of the 2 1 cycles. Okay? And so at the end, of course, you have that the topological invariants are the same. Why? Because the two objects topologically are equivalent. And so all topological invariants need to be the same. So if I take what is called the one-dimensional homology, I find one cycle here, one cycle here. But in the middle, I had 1 and none, 2 and 1, and then the end, 1 and 1. So the history of the cycles, of homology cycles, we call them, throughout this filtration of the two objects with the sub-level sets of a function, in this case height, can give us something which is qualitative as topology, but not so free as geometry is. Okay, and this is what we do in formal terms. Okay. But the idea is not just to see single sub-level sets, but to compare pairs of sub-level sets. For instance, here we make such a diagram by looking at zero-dimensional homology, meaning just pieces, connected components. And here I have 2, meaning if I take the sub-level set under level B, I have 3 components, but only 2 of them were already present under A. So this means these 2 in this area here. In this area, I have a 1, and here is the 1. What does it mean? If I take the sub-level set under level C, I get 2 components, but only one of the 2 components comes from components which were already present under A. And so I have 1. And so this is the region of 1. Region of 2, I can see that here I'll have 3, and so on. And what I get is a very particular representation of this function, which will always be with these superimposed triangles, and it's all determined by the position of these points and of some lines, okay? And so we can just compare. We can just compare those diagrams. Another way, actually 9 years after we started in Stanford and Duke University, they had a similar idea leading to the same type of diagrams, but starting with a completely different task. Our task was try to find particular functions to put on the objects, so that by taking sub-level sets, we can distinguish or say that or putting together objects. Okay. They had another idea. They wanted to know what the true topology, meaning how many real holes you have in an object, but just knowing a point cloud sampled out of the object, okay, which is quite normal. Either I take a picture so I have the pixels, or I have a machine touching the object and so giving me the coordinates of a grid of points. Always a cloud, a point cloud. That is very normal. How can I understand how many holes there are in an object if I have only separated points? Of course, that would be a very stupid topology, which would mean you have 1,000 points, okay, topology, 1,000 components. Very stupid. I know that there is something in between. So how could we overcome this problem? Put small balls around each point, each sampling point, okay? But what happens? Which radius for these balls? Okay, of course, first of all, make so that just one connected object comes out, okay? Yes, but when a connected object comes out, you might have this big one cycle, this circle, but you might have also these small holes. If you don't want yet to use measures to say big or small, but you just trust the fact that you are growing these balls around the sampling points, you can say, okay, at this level of my growing the balls, I get 3 cycles, okay? But if I make the radius of the balls still grow, I get that these 2 1 cycles get blocked, filled. Okay, so they were with the little persistence. The big one still survives, and you also have that a new one arises, unfortunately. Yes, but if you go on growing, eventually this will also be filled. Okay, and you must make enormous balls around the sampling points if you want to fill also the big ones, okay? Big one. So what you have is that in the growing of that radius, you have what? A cycle, 2 small, which live very little, another one which arises, lives very little, and one which persists all along this film, okay? This movie. And at the end also that ends. But it has persisted quite a lot of time, okay? That's why it's called by the Yankees, it was called persistence persistent homology, because it looks at homology object like the cycle, 1 cycle, 0 cycles, 2 cycles, and look at how long they persist throughout this process, okay? What they got was exactly the same type of diagrams that we got, okay? And, and we get some particular properties of these what are called persistent Betti numbers, which have these properties which say how these functions are appears when they are plotted in a plane, and also the fact that we can condense all this information into particular points. This triangle is represented just by this single point. This infinite triangle is represented by this line, and so on. And so this will be a simplified representation of this. And so we can compare these types of things, okay? Which is what we generally do by a particular distance, by putting bijections between the points of one diagram with the points of another diagram representing another object. And so we can find an optimal bijection with minimal displacement of these points, and this is called the bottleneck distance between the two diagrams. And this is good because if I take two similar but not two similar objects like this with respect to two functions defined on them, like ordinate in this case, we can say how much should I deform this into this. How can I measure my deformation? I can measure it like this by taking every point in X and finding what happens if I take the corresponding point on the other side and take the infinite norm difference of the difference of these, okay? And this is difficult to compute, but the distance between the persistence diagrams that we have with our way of putting things is a lower bound for this distance, and actually it is the best possible lower bound that we can get out of the diagrams for the lower bounds to that distance. And that is important, for instance, in image retrieval. Image retrieval is very important. Okay, I give a query which is an image, and I have a repository of images, and I want the most similar ones. All right, and so I need a distance. But distances are difficult to deal with. So if we get good lower bounds, we can say, okay, I don't know what's the real distance between my image and that image, but by making this distance here, which is easy to compute between the diagrams, I can give a lower bound, and I can say, okay, I just want the ones in a range of 0.8 from my query. This distance is 0.9. I do not know the real distance of that image from my query, but it's more than 8.9, and so more than my 0.9, so more than my 0.8, and so I can forget about it and not compute the real distance. Okay, and this makes computation absolutely incredibly faster than making the computation of all the distances, just giving good lower bounds to the distances by these techniques. And this is what we do in our way of doing what is called, and you'll find TDA quite often in now data analysis. Topological data analysis is mostly through persistent homology like this. Okay, actually we do there is quite a lot of things on variations on the theme. Okay, sorry. And there are also ways of simplifying the computation on the diagrams, and two are given by our team, two of these, okay. And but now we are going beyond and doing non-topological persistence, in the sense that out of data there are quite a lot of researchers which now are building topological spaces through what is called simplicial complexes, in order to use our techniques, not just ours, also our competitors. This persistent homology is very good at distinguishing and classifying things, okay? And so you find the researchers which do the most strange things in order to get persistence homology on their data. And it can be, one is one research, several researchers have worked on finding the importance of characters in a Roman, for instance. Okay, and there is Les Miserables, which is a benchmark for that. There's a wonderful depository in Stanford with a lot of objects which are already workable data, and one is the relations among the characters in Les Miserables. There is also Iliad, for instance, not touched that. Almost all work on Les Miserables, and that's one. So they built topological space on this in order to get to use persistent homology. Another one was a very interesting study on groups of languages, one of Europe and one of Congo, two groups of languages, to see the syntactical relations between these languages. And again, they were making acrobacies in order to get the topological spaces and use persistent homology on that in order to make classifications. And now what we are doing is going beyond that and saying, okay, we'll give you the possibility of entering all the machinery of persistence without the need of building topological spaces or simplicial complexes. And here I have my exposition, and okay, see you next Thursday for the midterm or end-term test. Ciao. Just a moment.